Okay, so we are looking at second order linear differential equations. The ones that we care about right now are in the form of ax double prime plus bx prime plus cx equals 0. Eventually, we will replace this 0 with other things. X is the dependent variable. We've got t as an independent variable. You don't see any t's in here, but eventually we will. But so x of t is what we're looking for. My solution is x of t. Oops, come on. Equals something. Okay. So I'm going to do this with an example. So let's take x double prime minus 6x prime plus 8x equals 0. Now, I'll scroll up a little bit to the previous one. Remember, we started with dp dt equals k times p, solved it, got poked, recognized x prime equals rx. Well, that's the same thing, gives me x equals ce to the rt, right? There's a general solution. These were some particular solutions. These were things that we could solve. And then we said, oh, snap, these second order ones are really similar. They've just got an extra derivative piece here. So this is the key. I'm going to attempt something. I'm going to take a trial solution of x equals e to the rt. We are trying this guy because we knew that it worked in that other one, that previous one. It's just like a process of recognizing a pattern and guessing our way into a solution. So when I try x equals e to the rt, if I can figure out what the r values are, or r value is, or r, then I know what my solution is. If this is x of t, then that would replace this guy right here. I need to get an x prime and an x double prime. So x prime is, r is a constant, remember? So I get r times e to the rt. X double prime is r squared e to the rt. It's just some chain rule there. So now what I'm going to do is do some replacement. This guy will replace that. This guy will replace that because it's the derivative. And then this one will replace that, well, I guess that whole thing, because it's the second derivative. So when I plug those in, I get r squared e to the rt minus 6 r e to the rt. That is this guy with this negative 6 on it, plus 8, that's this, times this, e to the rt, and I need that to be equal to 0. So it looks kind of complicated at first until you recognize that that term, that term, that term, all of them have an e to the rt. So I can divide everything on both sides by e to the rt. When I do it on the right side, I just get 0 over e to the rt, so it's still 0. And that gives me something that's really nice. R squared minus 6r plus 8 equals 0. This has a name. It is called the characteristic equation. Literally, we will learn so many different ways to come up with solutions to these things. They're all useful in different scenarios, but every time it takes us through a characteristic equation. So, anyway, look at this. I want to solve this. Oh, snap, it's a quadratic. I know how to solve quadratics. What's the first way I try to solve quadratics? Usually, I try to factor. So let's try to factor this thing. What do we get? We get r minus 2 and r minus 4 equals 0. What's that give me? R equals 2 and r equals 4. Now you may say, wait, what's r again? Well, remember, this line right here. I use that trial solution. So now I know that the R values of 2 and of 4, they actually fit. They fit this equation, or they should if I've done my math right. So that means that x of t should be, if I've done it right, sorry, I'm going to write it a little bit different. I'm going to write x sub 1 is e to the 2t, and x sub 2 is e to the 4t. Now, those are two different, there should be an equals. There's two different versions of x's that would fit. I took these two values and plugged them into here. My general solution is x of t equals c1 e to the 2t plus c2 e to the 4t. Let me back it up to some things we talked about before. Remember, you may say, wait, where'd the c come from? There wasn't a c when you did this stuff. Well, I got two arguments. One, I didn't want to put c's here because I didn't want to junk up our equations. But go back to this one. That one got a c from separation of variables work up here. So if I come back down here, it's like, all right, it seems reasonable that this would get a c. But think about it. If I were to put a c here, it would show up here and here because it's just a constant, which means that it would show up here and here and here. Do you follow that? And that means that I could divide it out and just put a c here. So it would still work if I had a c. So in fact, c1 e to the r, or c e to the rt is our solution. And I have two different solutions, a 2t and a 4t. So c1 e to the 2t and c2 e to the 4t. Why does this also make sense with what we did before? Well, we said there's two principles. One, this seems like it makes sense, is what we were doing down here. And then two, I need to have two c's because I'm essentially, by solving this thing, backing my way into finding an integral solution to this where I've integrated twice. And I should have those two integration constants. So come down here. This fits those ideas. I used my pattern recognition to say, bam, I know that should work, might work. And then said, all right, well, what do I get? I get two of them. Oh, this one, that one, both get a C. Sweet, two C's, yay. So let me convince you that this works. I am only going to do it for, I am only going to do it for this one because it'll be easier to see. What I do would also work for this guy. I am going to plug that into this equation. So notice, I've got x double prime, x prime, and x. So let me take x equal to c1 e to the 2t. What's x prime? X prime is 2 c1 e to the 2t. What's x double prime? Well, that is 4, c1 e to the 2t. Just some chain rule. So now let's plug these guys in. We will, let's see if we can color code it. This guy is, come on. This, there we go. This is that. And then, let's see, the next color is blue. So this guy is going to go in for that. And then the next color is green. Or no, so the next color is purple-ish. Purple goes in for that guy. So what I've got is x double prime minus 6x prime plus 8x. Well, that is equal to 4c1 e to the 2t. That's my green. Minus 6, that's part of the equation, times blue, 2c1 e to the 2t, plus 8 purple, c1 e to the 2t. Well, what is that equal to? Well, look, everything has a c1 here, here, here. They all have a c1 e to the 2t. So I'm just going to factor that out. And what do I have? I've got 4 minus 6 times 2 plus 8, which is equal to C1 e to the 2t times 4 and 8 give me 12. 6 times 2 gives me 12. Well, that's 0. And 0 times that thing up there, it's 0. So what I want you to see is that this thing here, this guy right here, does actually fit this equation up here, because I started with the equation, I did some stuff, blah, 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 and I got 0. So that means this equation is equal to 0 when I plug in this value right here. So that is our general strategy, check mark, that's good, for solving these things. You will quickly learn some shortcuts. You may already see them, but what you're going to do in a moment is go rock through a handful of these with different sets of directions, and you'll see that in a moment. So hopefully this strategy makes sense. Let me briefly run through it so you see it. Summarize it. All right. Differential equation. We try x equals e to the rt. Take the derivative twice. Then plug those pieces in to the original equation. Wha-bam! Equals 0. Oh, nice. I can divide out by e to the rt. That gives me a polynomial, quadratic in fact, that's easily factorable and gives me a pair of r values, and those r values are two different individual solutions. And in fact, I can multiply the front side of those each by ac to take care of my issue of having two integration constants. And then this right here, this is my answer. That's my solution. Okay? And this blue work down here is just to check to verify that this is working for that. And you could do the same check with this and you would get 0 as well. So hopefully that makes sense and you can rock through some of these in groups or on your own.